All right, we're live. So it is Thursday, July 24th, 11 a.m. Pacific, and this is DB Hangouts. Today we're going to be talking about more indexing, and hopefully we've got Morgan today who is promising me some cool stuff with spatial indexes. And we'll see what else we can get around, though. So if we want to do a quick round of introductions, I'm Jeff. I'm a DBA at Box.
Jeff, I'll go next. My name is Morgan Tucker. I'm MySQL Community Manager at Oracle.
Hi, my name is Shlomi Noach. I'm engineer at Outbrain.
Okay, so yeah, last time maybe we had I would consider it a deep dive, at least initially, for people who haven't had to learn about indexing before, and just how all the data structures work, kind of the things that are in there. Tim Callahan from Tokutech talked about some of the stuff that TokuVD is doing with fractal indexes, so that was kind of cool. And we kind of got stuck on spatial indexes. Like, everyone's heard of them, everyone's like poked them a little bit, but no one's actually really used them before. But we do know that they're also, Oracle has been telling us that it's greatly improved in newer versions of MySQL. So I mean, I don't know where you guys want to go. Do you want to start on spatial indexes? Do you want to talk about more just general indexing stuff? I mean, Shlomi, you weren't here last time, so if you want to talk about just indexing for you and what kind of stuff you do around it, that'd also be a great way to start.
Yeah, I'll be happy actually to hear a little bit about GIS because, yeah, to be honest, I never actually worked with GIS with MySQL. Maybe I'll describe later on how I use GIS with Sphinx Search, but I never actually used GIS with MySQL, so I'm curious.
Okay, Morgan, you're on the hook now.
So I'm trying to rope in a colleague of mine to assist me. He's just stuck on another call. If he becomes available, that might be the best way to handle it. Okay. What I thought, though, that I might be able to offer and I might be able to fill in is Tim talked about the B+ tree index of InnoDB as a way of describing the fractal tree index that comes with TokuDB. And he mentioned a couple of things like the insert buffer and how, in comparison, comparing Tokutech to InnoDB, InnoDB is actually not too bad at a couple of things. So on offer, one thing I can describe is I can describe how the insert buffer works with InnoDB and some of its performance characteristics. So we could go from there, or we could start a little bit more general and talk about some other pain points. Have to open it up for Shlomi and Jeff.
Insert buffer sounds good to me, unless you want to talk about something else, Shlomi.
Yeah, that's cool. Go for it.
Okay. So let me see if I can figure this out. I'm going to share my screen. And okay. Can you see my screen? No problem at all?
Yep, looks good for me.
Yep.
Okay. So this is a simulator of a B+ tree, InnoDB's index type. And I'm going to build a pretty simple tree. Let's start with inserting the number 50. And really pretend this is my primary key and there's some other data that's associated to it that's just appending to the end of that 50. And so 50 is my first entry, and this results in one index page. I've said here, just by clicking this little radio box, that a page can only hold 3 items maximum, and then at that point it splits, just so that we can get a lot of growth in this tree. But in reality, if you're looking at something like InnoDB with a 16 kilobyte page, you can get thousands of entries per page if you have something like a 4-byte primary key. So inserted 50, let's insert value 1. And this just expands that existing page. So now my first page has 2 values. And now let's insert value 100. And we can see that we have a split where we go from having just one page to now we have a root page. And then at our first level down here, we have one page that has the value 1, another page that has the value 50 and 100. And if we're doing our binary search to be able to find a specific value, when we start at the top at the root page, if it's a value less than 50, then we make this decision to head on the left side of the tree. If it's greater than 50, then we go to the right side of the tree. B+ tree indexes have the ability to go next as well. You can see this arrow here. And so this just basically means that we can do a range scan or a table scan across our leaf pages here without having to go back up the tree to be able to find the next value. Let's make the tree a little bit bigger. It's not very interesting how it is now. Let's insert value, let's call it 25. Question from Shlomi, have I discussed primary keys versus secondary keys? I don't know if we really have yet. We did mention that InnoDB, everything is an index in that it has a clustered index, but not necessarily the specifics. Okay, and this is, you can probably see it show up on my screen, maybe not. Someone's just pinging me on Messenger. Okay, so I inserted value 25, so this ends up being inserted on the left side here. So on one page I have 0 and 25, on the next one I have 50 and 100. That's inserts something like 26. And 26, we can see what happens here. This page gets too big, so then it has to split. And the root page, it has free space, so now it is modified to say less than 25, go to page number 1 on the left-hand side here. Between 25 and next value, there's this middle page here, and 50 and above go to this page on the right-hand side here. So one thing that I think is interesting to point out here, as I'm going to insert just a few more random values to expand out the tree, is that B trees, they're really fat, they're really wide, they're not very deep. If you are familiar with doing little exercises where you might have something like a binary tree where it's just individual single nodes, they can get quite deep quite fast, but a B+ tree, it's only ever really 3 levels deep or 4 levels deep in production if you have a short primary key. Based on that, there could be millions of this very lowest tier of what we call leaf pages for what could be thousands above of what are the index node pages. So one thing that Tim pointed out was that performance often tends to be that not all of these leaf pages, the bottom tier of pages, can fit in memory. And this is where you get to see a bit of a drop-off. So what InnoDB has is something called the insert buffer. So I'm going to capture this tree that I've created here. I'm going to copy it, and I'm going to paste it in Photoshop. And then I'm going to have to change my screen input so that I can keep you on Google Hangouts while I draw on top of this tree. So just hold on for a second while I try and manage this process.
Photoshop.
Still with me so far?
Yeah, we're still here.
All right. Okay. And let me just try and change my input. Okay. How's that working?
Looks pretty good for me. How about everyone else?
Yep.
Yep, you got a thumbs up. Go for it.
Excellent. So just make this a little bit bigger. Let's say that as a result of only having a finite amount of memory, this page is in memory. This page is in this page is in memory. This one is, but this guy, number 25, is not. And let's say that we want to do an update, and these values that I'm showing here, I'm kind of pretending that that's the primary key value, and as I said, there's extra data that's associated with it. So let's pretend we wanted to do a query like update my table set column A equals new value 25. Something like that. So usually what I would have to do is I would have to navigate this tree by starting at the root page, saying 25 is less than 26, so that I would follow it down to this index node level 1. And then I would say 25 is going to be the right-hand side of this value, because 25 is greater than or equal to 25. So I end up finding that I have to load this page into memory. And then I have to patch that page, make the modification, and I have to write it back to disk. And so I'm going to have a performance problem that I suddenly have to load this page to be able to do that. But if column A doesn't have any restrictions on it, like it doesn't have to be unique or anything like that, I don't necessarily have to make that modification straight away. What I could do is I could make that modification next time that page is loaded into memory instead. The real trick here is that it can't be a unique index, but it could be an indexed column. And so what InnoDB will do is it'll have a feature where it'll discover that this page is not in memory, and it'll build a secondary tree just off to the side. And it'll say, of modifications that I have to make, I have to make a modification to page 25, page with value 25, next time that it's loaded in memory. And so every time that the page is loaded into memory, it'll check this insert buffer, this secondary area, just to make sure that there are not any pending patches that have to be made before the values can be returned to the client. So from that perspective, it's a completely safe feature to be able to buffer or delay these modifications. And if there's free idle capacity, what InnoDB will actively do in the background is it'll look at the insert buffer, it'll find out what changes are pending, and then it'll load those pages in memory and make those patches, and then write them back to disk.
So Morgan, a question?
Yeah.
So you were saying about whether this is or isn't a unique key. What's the relevance of the key being unique here? I mean, the call A value is not the one being indexed, right? We're speaking about the primary key ID equals 25. That's the part that relates to the search, but that the update query doesn't modify the index itself, right? It doesn't change the structure of the index. There's no new index node here. So what's the relevance to the index being unique or not being unique?
Yeah, so I probably made a little bit of a simplification in that if the column was indexed with just a secondary index, it would have another tree that has to be modified. And in my picture, I'm really just drawing the primary key rather than the two sets of trees, which makes it confusing. But from the perspective of uniqueness, if I made a modification, it could violate a constraint, and I don't have the ability to check that constraint if the relevant data is not in memory. So if you've seen something like MySQL dump, how it does set unique checks equals 0, what it's actually doing is it's allowing the insert buffer to work for unique indexes, which it wouldn't by default for InnoDB.
Okay.
So oh, please go on.
So is there an insert buffer per index, or is it like shared for a table?
In the actual implementation of where it's stored, it's all stored in IBData1 in the central table space. We've discussed the ability to have separate table spaces or separate buffer pools or things like that to be able to have dedicated space for the insert buffer. But it doesn't exist at the moment.
So, like, all the insert buffers for all indexes, for all tables, are in the major InnoDB table space file, right?
That's correct, yes.
Okay. And what kind of lockings are there on the buffer? So what should I be expecting?
I can't think of anything specific around locking, but the big concern that you can have is that, well, to start with, if you do have all your data in memory, it's not going to be so useful. So you do have the ability to disable that. And in some cases, if you're not going to make approximate changes to the same pages in succession, it's not so useful because it can't reduce I/O, which is the main actual feature of this insert buffer that I've not described. And in that case, it can actually consume memory in the buffer pool by having this feature. That's the main caveat I can think of. I can't think of locking if that was.
Yeah, so I'm just maybe I need to think this through because of the balance between I/O and memory. But say, okay, with MySQL 5.5, we can split the buffer pool, right? I can have multiple buffer pools, and at our company, it already proved to be extremely useful when we split the buffer pool on replicating slaves. That really boosts the ability for slaves to both serve and replicate. So I'm just wondering whether the insert buffer, just holds back the any concurrency benefits that are available due to the multiple buffer pool.
Gotcha. So it should be able to take advantage of that split buffer pool feature, no problem at all. The reason being is that what multiple buffer pools does is it essentially hashes the space ID number and the page number to be able to find out which buffer pool that page is supposed to be loaded in. And the insert buffer stores things in regular InnoDB pages, just like these index pages are that are on the left-hand side of my screen are. So it won't have its own reserved buffer pool. It'll be hashed amongst the multiple buffer pools, same as the regular indexes are.
Okay, that's pretty cool.
Yeah, and it's not like a tree in memory, right? It's just pages at the end of the day, just like any other page in the buffer pool. If you look in the InnoDB buffer page table in information schema on a recent version of MySQL, it will break down the pages that are in memory, and there are these ones are called iBuff something page, basically, so you can see each one of the pages that it takes up.
And just to confirm, Mark, that table, that's the one that if you have a very large buffer pool, you need to be careful with querying, correct?
You definitely need to be careful with it on a very large buffer pool, yeah.
That was introduced in 5.6 for reference with recent versions.
Yep.
There we go. Yeah, I remember. Yeah, I think you demoed that last year at MySQL Connect with some of the enterprise monitor stuff that would draw out.
Yeah, that was breaking it down. Yeah, and that actually shows you exactly how much the insert buffer takes in the system space on that as well.
Yeah, very cool. I'd be scared to run that on my system right now.
If you have a lot of memory, then yeah, you need to be careful. And it's all down to that lock-in again, right? Each one of those pages in the buffer pool, they have to, whenever they're accessed, they're locked with the buffer pool mutex. So every one of them, or with tables and the insert buffer, and literally anything that's in the buffer pool, the fix for concurrency on that is to try and increase the number of buffer pool instances.
So actually a good question, just since we're talking about multiple buffer pools, is what kind of values have people seen work for them? Because when we were testing it out, I think we ultimately settled on 8 buffer pool instances in a server. Seemed kind of like the best place to get the most throughput without any significant change. I'm curious if anyone else, probably you, Shlomi, if you've seen any difference in the number.
Yeah, I've tried the 8 instances that work pretty well. I've also seen this heuristic of saying 1 buffer pool per 2 gigs of memory, which we're doing, and I can't say I saw a lot of difference, but I'm sticking to this one because it works well for me. So
Okay.
with larger machines, we have more instances.
It's worth pointing out that with 5.6, the default is 4 instances as soon as the buffer pool is larger than 1 gigabyte RAM.
Okay.
And this is the way this works, as I sort of described before, is that InnoDB will hash the page to be able to find out which buffer pool it's supposed to use internally. And this is a way of reducing some of its internal contention, its internal locking that happens. And it was a hot spot in prior versions when you were running on multi-core machines.
Yeah, on a particular use case we had, so where we saw the effect of multiple buffer pools was, like I said, on replicating slaves. We would see slaves lagging, and we would investigate the machine, and CPU is idle, and I/O is idle, and seemingly the machine could produce a lot more. And the answer was with the buffer pool. We used performance schema to diagnose that. Yay! We saw how much time we were waiting on the buffer pool mutex. And actually, we did find out in our particular case that below 8 was not good enough. I mean, 8 was the starting point for good performance. So just sharing my experience.
Yeah, that's really interesting. Maybe Mark has some thoughts, because slaves tend to be a little bit more single-threaded, but maybe if you have reads on those slaves, it's doing page replacement or something like that. It needs to hold the...
No, I mean, the slaves were serving at the very same time, right? So they were doing a lot of reads while the slave was doing writes.
Right.
So,
and
that's definitely going to be an issue, and normally because of a single-threaded slave. I mean, you might see better performance with lower numbers of buffer pool instances and concurrency with more slaves. They get the chance to get more work done, basically.
Right.
Well, what I've seen, for the most part, is around about 8 for any decent-sized buffer pool. So like 32 gig and up to 64 is it seems to be around a normal and seems to work well. Most people go up to like 16. The max is like 64. But I don't really see many people getting much benefit over like 16 generally. I mean, it could happen out there. That's why it can go up to 64. And we originally came up with that heuristic of, it was originally 1 gig per buffer pool instance, but it's gone up to 2, roughly 2 gig seems to work. And if you go in 64 and 128 and above, then test it out, right, and see what works for you. That's the best thing to do.
Yeah, when we tested it out, we went from 1, 2, 4, 8, and then 16. I think we did 32 as well, and we found that once 8 was kind of like the sweet spot for us with a lot of our data set at the time. 16 and 32, there wasn't too much of a change from 8, so we decided just to leave the hash at 8. But I'd be curious to revisit that with some of the minor version upgrades we've done, and actually when we do our 5.6 upgrade, when we finish rolling that out, maybe you know offhand, like, because we're running Percona 5.5 with this patched in. Does 5.6 bring any sort of significant change with it, or the way that it works maybe with moving things around in memory?
Not really. Not that I remember in 5.6. Not the way it moves things around or anything like that. That didn't change significantly.
My memory's already focused on 5.7.
There's changes in 5.7. Yeah.
And I can think of a few. Yasufumi wrote on the MySQL Server team blog just a couple of months ago about improvements to DML workloads, and particularly the things about flushing operations has changed in 5.7.
Yeah, taking account of all of the buffer pool instances themselves, and other things like when you dump the buffer pool as well, you can dump percentages of each of the buffer pool instances now as well. So you can do things like take the most recent 10% read pages out of each of the buffer pool instances and dump those off instead of trying to dump off the entire set. So it's a lot smarter in how you can actually dump pools to actually reload a lot quicker your working set into memory as well.
That's pretty cool. So I think I want to pull the reins in and get us back onto indexing, because buffer pool instances is, again, it feels like another topic that we could just kind of run with for a long time, and I kind of want to save it for when we have a few more people. But so something I want to ask you, Morgan, with the B plus tree kind of stuff that you had going was, I mean, yeah, what does this look like for secondary indexes? Is there an insert buffer that's used for secondary indexes? And I mean, maybe that's something we can.
Yeah, I kind of mixed this two to add some simplicity, but the insert buffer only works for non-unique indexes. So it would be for the secondaries there. If you had we haven't really clarified what's the difference between a secondary and a primary index, but basically a primary index is the primary key and a secondary is everything else, so it would be unique or non-unique. And InnoDB can use the insert buffer for unique secondary indexes, but you need to turn on that option that MySQL does to be able to do that. And the reason purely for this is to make sure that it's completely safe.
Right. I don't know why. When you said unique, I was thinking strictly unique key indexes. I didn't even primary keys, obviously. But okay. Go ahead, Mark.
The primary key is always going to get into memory. Any change to a row that you make is going to pull the primary key into the buffer. I mean, the insert buffer is purely there to stop the I/O of every secondary key that isn't unique when you actually make the change to the pages.
Right. So how does insert buffer work when you're dealing with things like gap blocks potentially? And I mean, because ultimately you had said, Morgan, if something's read in, it checks against the insert buffer to see if it needs to apply any kind of in-flight changes that haven't been written into the actual page yet. But if I'm running a query that is maybe locking a good chunk of stuff off secondary indexes and therefore performing some sort of gap block, if I have a repeatable read isolation, does that change any of the semantics around that?
I guess to paraphrase your question, because it might not be specific to insert buffer, do you need to load a page into memory in order to kind of lock that range? So there could be a whole series of data that's in pages, and that data is not in memory, but you need to imply a gap block for that. I don't think that has to be in memory. Mark, do you have a better answer?
But the lock or the page, you mean? I mean, the lock will be in memory itself. It doesn't necessarily have to bring the page in there, but if it's reading the index itself, which will be the gap block, right? It will be reading by that index for something. Then it's reading that index, right? It's going to bring it into memory because it's trying to read those index pages to satisfy something. Otherwise, the locks will be on things like the primary key itself and doesn't necessarily need the page. That makes sense?
Yeah, no, that makes sense. Okay, so I guess maybe just kind of opening more generally, if you guys want to start talking about maybe just secondary indexes and things around that.
Yeah, I have a couple more questions about the insert buffer. So is it like linked list in memory, or I mean, is there a special construct to it?
No, like I said, it's just pages in memory. So
just pages.
There are lists, right? There's the LRU list and the free list and all of those kind of things, and they're managed in the same way in the buffer pool.
Yeah.
Okay, so what? I'm sorry. Go ahead, Morgan.
Yeah, and insert buffer pages themselves, being pages, they can actually be evicted from the buffer pool as well if there's not sufficient memory. Okay. And they use the redo logging system as their modifications are made, like everything else in InnoDB. So it's safe if you have a crash and you come back online.
Okay. So the next question is, some queries will have to first go through the insert buffer to satisfy the most recent changes, right? what are those types of queries that will have to first go to the instant buffer and only then do the real math?
So what happens is that when you load, you run a query as you need to run a query, and when you load a page into memory, you will check the insert buffer to see if there's a pending modification that has to be made. And I should clarify that I called it the insert buffer because that's what I've been comfortable with, but there can be pending changes that have to be applied for inserts, updates, and deletes, all pooled in the insert buffer waiting. So as you run your select query or your delete query, as that data is loaded up, before the results are sent to the MySQL level, those patches or those pending modifications are made from the insert buffer.
But is the type of queries that's going to be affected? I mean, if I query for data,
yep,
then it doesn't actually matter, right? The instant buffer is irrelevant to the answer itself. But in terms of which index to pick or stuff like that, is that something that the optimizer is any of this taken being affected by the instant buffer? Or, does anyone actually go to the instant buffer to check around stuff?
The optimizer isn't aware of the insert buffer. It's too low a level. It's completely different layer. The kind of things that will be affected by the insert buffer are queries that are trying to use those indexes themselves. So, I mean, it could be any query, right, at the end of the day. Right. Anything that tries to use that index to satisfy statement X.
Yeah.
Those are the ones that are going to be affected for the most part.
Okay. I guess your question is kind of like when you were asking about the optimizer, could statistics be out of date because you're looking at a tree that is not really the real tree, it's got pending stuff to make? Well, if you updated the statistics and it had to do its random dive through, that act of doing that would probably repair the pages that were the random pages. So it's really a low-level implementation of a deferred modification that will happen any time that page replacement happens, anytime it has to load something in memory. Or if there's sufficient background capacity, it'll quickly jump in and start doing what it had to do.
So something I'm curious about too, is it possible to have multiple changes stacked up for a single page inside of the insert buffer? Or does it swap out and replace it with the newest one?
That's the aim of it. So the aim of the game is that you have sort of like clumping of modifications, so that often in real life data sets you will have these hotspots, and you can merge them together in the insert buffer, and then when you need to load that page up, you can write all of those modifications back as one.
Right. So I guess what I was getting at was, if you make a change you have a change pending for a page that goes into the insert buffer, and then another change, does that get just added to like a list structure that they are then merged down, or does it kind of swap it out?
It discards the old change and replaces it with the new one. So if you look in Show Engine InnoDB status, there's an insert buffer section.
Gotcha.
With an insert, it's always just going to push it in there, right? It's an insert, it's a new page, it needs to be created. But with any kind of DML, so an update or delete, you can see a couple of different statistics that are reported there. One of them is a discarded stat for each update and delete, and the number that they've actually merged themselves, right? The merge is the process of taking it from the insert buffer down into the pages themselves. The discarded thing is it actually overwriting a page with some data before it was flushed out to disk anyway.
Gotcha. Okay. Now, is that something that someone just running a database server would want to actually be cognizant of or kind of look at? Or is that just kind of there as a nicety?
It's actually, in many ways, not much different to just normal pages, right? A lot of the time the pages are just updated in memory, the working set's in memory, and it gets updated in memory, and gets checkpointed to disk at some point in the future, right? The point is to try and limit as much I/O as possible and stack up those changes in memory, but still be able to recover it all from things like the redo log.
If I paraphrase your question, Jeff, and let's say like list of risks, if you did not set InnoDB I/O capacity correctly, and you left it at default or something like that, then you might have too much insert buffer and not enough actual modifications, and that would be something that would be annoying because a large part of your buffer pool might be consumed with insert buffer.
Got it. Okay, yeah, and like you said before, the insert buffer is one of the things that gets kind of evicted as memory is needed inside of the buffer pool, correct?
It will use the same LRU as regular pages will.
Gotcha. Okay. Cool. I don't know what else to ask about insert buffer then. It's just this, like, it became very clear all of a sudden.
Yeah. I was thinking about it earlier today. My colleague Matt had told me he might be late for being able to describe GISs, and I was thinking I can fill in and I can describe this. It's certainly a very useful feature.
So you had mentioned that it's possible to disable it or to change some of the behaviors of it. Just out of curiosity, what would those status or those config variables look like? Are they all insert or iBuff or insert buff something?
No, the main one would be I/O capacity that you would change.
Gotcha.
And that would basically do more merging of the insert buffer back into that main secondary tree in the background. InnoDB change buffering, I think, is the name of the setting, where you can choose that it can do inserts, updates, and deletes, or just a smaller subset of that, or none of that. The configuration for I/O capacity, I think, was first introduced in InnoDB plugin. So for many users, that meant MySQL 5.5. And the same with the change buffering setting. I think was plugin / 5.5.
Okay, cool. Yeah, I'm writing that down real quick, sorry.
No problem. And actually, TalkUtech, it's a shame not to have Tim this week, but they have a benchmark called IO Bench, where they show the performance of inserting 1 billion rows into a table. And insert buffer, if you disable it, it does take a lot longer to insert into an InnoDB table.
Cool. Shlomi, so do you have any other answers about the any other questions?
No, I'm good.
Okay.
We should probably move on.
Yeah, I was gonna say, is there other stuff around the world of indexing? I mean, maybe for you, Shlomi, is there anything that you do or indexes that you favor or avoid, maybe when working with database schemas?
Wow. So I don't know if you've discussed this last week. It's pretty important to know about the difference between primary keys and secondary keys with InnoDB. So have you discussed this? I'm guessing not.
Yeah, I don't think so much.
We really have.
Okay. So very briefly, and I don't have these fancy drawings Morgan has just presented. Generally speaking, with indexes, you can speak about clustered indexes and non-clustered indexes. And non-clustered indexes is easier to describe. Like, you would have a table on one side and then an index on the other side, and all the data is in the table, and the index would just point to those rows of data in the table. That would be a non-clustered index. And you could have multiple indexes like that, and they would all point to the same set of data, which is, somewhere to the side. Whereas a clustered index is slightly more confusing, because a clustered index actually includes all table data. So there's no entity of table residing somewhere out there. It's just embedded within the clustered index. Like the leaf nodes of the clustered index is not pointers to the data, it's the data itself. That's the leaf nodes with a clustered index. So with the InnoDB, you get one clustered index per table, and that's the primary key. Theoretically, you could have multiple clustered indexes per table, and I do believe Tokutech support or used to support that. I'm not sure. I'm not authorized on this, but with InnoDB, it's just one. There's one clustered index. That's the primary key, and that's where your table data resides, right? It's within the primary key. And the question is, okay, what's going on with the secondary keys? How do secondary keys point back to the data which resides within yet another index? How does that work out? Yeah, I can see Morgan.
I'm going to try a picture. Let's see how it works.
Cool.
So
go ahead.
The primary key here. This is out PK. It's kind of like RK. And this is my secondary index. And even though I've got the same values, ignore that for a second. If we were trying to find select star from my table where ID equals 20, well, then we navigate the primary key. We find value 20 somewhere, and then piggybacked in the end of that value would be the data. So a primary key lookup is just one tree traversal, finding that leaf page, and then returning the data. It's quite efficient. If we did a secondary key lookup where we said select star from my table where username equals Morgan, username might be a secondary key and ID might be the primary key. We'd have to navigate this secondary key index, find the value Morgan, and then in the value Morgan, the sort of payload for that, the data, would be that's ID number 20. When we have ID number 20, and I can't draw, then we could navigate the primary key, find value 20, and then return the payload. I guess it's the way that would work with a secondary key.
Yeah.
I hope that helps with the diagrams.
Good work.
Thank you.
So the side effect, or the main effect, is that any secondary key lookup actually includes a primary key lookup, unless it's a covering index and it serves the entire answer. You're just searching for columns that are covered by that index. But if you're generally looking for, give me select star from some table where secondary key value equals 10, that involves a primary key lookup. And that's pretty much pretty important to remember. It's like you take a cab somewhere, right? And the meter starts with a $10 charge. That's the minimum wage you're going to pay for that cab. And as you go along, you may pay more, but the $10 is guaranteed. That's the price you're going to start paying. So the same goes for primary key. The price to read, to go through the depth of the primary key from the root, which is typically which is in memory, and some of the nodes could be in memory, but eventually at the end of the day you have to dig down and get into a leaf node. That's the minimum price, that's the minimum wage you're going to pay for your lookup. To this, you add the payload you need to, you get charged for looking up the secondary key. And one important outcome of this is that you really typically want to have your primary key as shallow and as small and as cheap as possible, right? So for example, an integer primary key like an auto increment plays nicely into that role, whereas a primary key over I don't know, a URL, right, is typically not so good in terms. it might serve well for a particular workload of queries, but generally speaking, it's an expensive primary key, and all other indexes are going to have to pay that price and then some for your queries. So,
I drew my tree as well, Shlomi. I have an opportunity to describe adaptive hash.
cool.
Another InnoDB feature. So, yeah, absolutely. As you described, the secondary key indexes, they are more expensive because they, unless you can grab all your data from the secondary key index, they do imply that you have to do a primary key lookup as well. So it's two tree traversals rather than one. So what InnoDB has is that if you have secondary key values that are very frequently accessed, and I think very frequently means 20 times in a short frequency. It has to be quite a high number. It allocates a special little set of pages that I'm going to draw at the top of the tree that it calls the adaptive hash. It's not a complete set of what's in this tree below, but just the hotspots, where if you're looking for something like, in my case I said user ID equals Morgan, if that user ID equals Morgan is very hot, before you do the tree traversal, you can look in the hash and say, well, that was hot. User ID equals Morgan refers to this specific primary key page here directly. And so it skips the secondary key traversal and actually skips the primary key traversal, and it's just a reference directly to the leak page of the primary key. And that feature's on by default in InnoDB.
So it points directly into the leaf node of the primary key?
That's right.
Oh, that's nice. So how does invalidation work out? I insert a new, I delete a row. How does that go now and search all the adaptive hashes and looks for that row and purges it from the hash?
I don't know the specifics, but it is safe, and it does mean more housekeeping as a result of having to keep that direct link to the leaf page. So in some workloads, the adaptive hash is worth disabling because the housekeeping can create some mutex contention. That's certainly been something that's been discovered over the last few years. Cool. I think Percona has a feature to be able to hash the adaptive hash to reduce some of the mutex contention. I don't know if it's directly available in MySQL releases.
Cool. So Jeffrey, you were asking, whether there's types of indexes I would avoid. I typically don't like, unless it's a data warehouse table or something that by design is supposed to be very fast. I don't like to see primary keys with 3, 4, 5 columns in the primary key.
Yeah.
In fact, I often find that this leads to a lot of contention. When I approach, when I used to do consulting, I saw plenty such cases, and they would approach me and say, "Oh, yeah, okay, but that's the natural key we've got. And we have no other natural key." And my answer would be, okay, so why don't you invent one in the form of an auto increment primary key and turn what used to be your primary key into a unique key? Now, we've supposedly increased the number of keys and the number of, the amount of housekeeping for that table, but that actually reduced contention, reduced locks, because the primary key was thinner and lighter. And I'm sure Morgan would explain better than I why that would work out so well, but it does.
Yeah, so actually I thought there was a feature in MySQL where if you didn't define, maybe it was only when you don't define a primary key, but I thought there was something where it automatically creates an integer.
When you don't define a primary key, InnoDB would pick the first unique key it finds, and if there isn't such one, then it will use the internal row ID or whatever identification.
And Shlomi, I think you can describe the problem that creates straight off the B-tree visualization tool that I pulled out, because it'll make your tree much deeper rather than fat, which is what you want.
Yeah.
Yeah, and to actually, so something I'm more curious about then is, and maybe Mark or Morgan, you know this, but like, what is kind of the upper limit on a primary key that you can have? Since that, you know, if you do like a bunch of like text-based fields, it's not text, but character type data, because I know there's an upper limit on the amount of like a varchar you can put into a key.
Yeah.
So is that the same for primary keys? Is it actually less because it's now being a payload inside of secondary indexes, or?
I think there's two questions, which is a actual limit and a practical limit.
Sure.
I don't know the actual limit off the top of my head, but it would have to be less than half of 16K, based on that it has to be in the.
I think it's around 768 bytes, actually.
Okay.
I think. I could be wrong.
Yeah, or 755 or 756, something like that.
Yeah.
I encountered it with a schema yesterday, so.
That makes sense.
And it's the same with a primary key as it is any other key. It's an index limitation. It's not necessarily a primary key versus normal index limitation. So it's the same on any of them.
But the practical limit for performance might be quicker than the actual physical limit, because if you look at 768 bytes and you divide that by 16K,
right.
There's not many values that you could fit per page in an index if they all take up that length. So I believe if it's UTF-8, those values are going to be variable in length in the B+ tree. It's not something I know for certain, but if it is very wide, the tree's going to get deep, and you want the tree to be, as I said, fat.
Yeah, and it's not even dividing 16K by 750 whatever, or 768, whatever it might be, right? Because part of a page is always reserved for extra space as well. So I mean, it just gets amplified because you're not filling the entire page; you're only filling a part of the page too.
Got it. Yeah, that makes sense. And so yeah, I guess kind of just to tack on to what you were saying, Morgan, is you ultimately you want to drive down, or you want to pack those pages more tightly, and just realistically, and having a smaller key allows you to do that. And that's why typically, yeah, just an integer, probably unsigned. Auto increment, that's going to solve your problem, and if you start getting into big workloads, like I remember when we had to internally change the identifier for files in our system from an integer to a big integer, just so we had enough, because we were coming up to the limit of 2 to the 31. And I mean, just the space concern that you start thinking about then, you're increasing a key, which means all of your secondary indexes are going to get a little bigger, your primary key index is going to get bigger, and how many servers is this on? How many tables is this on? It's a whole lot of amplification that you need to be cognizant of.
Yeah, I mean, it's not even just the key with a primary key, right? I mean, you've got the data in the page anyway, right? You're storing the data, so if your data is that size, your data is that size, and it's going to be in those pages or linked off to other pages, depending on the type, right?
With long text and blobs with the overflow.
Yeah, or even a long varchar or something like that as well, right? They're going to push those off to different pages as well. But otherwise, you know, with the primary key, the data is there. I mean, it doesn't matter because you have to store the data along with the PK value anyway. It's on the leaf page within ODB anyway. It matters more with secondary keys for all of that kind of stuff to be able to pack more values in, and even more values on disk, right? That's the other key thing is because we're storing the primary key along with the secondary key value. We've actually got the primary key value in there. It inflates not just things in memory, but on disk too. So the longer it is there, the more you multiply it on every secondary key as well.
Yep.
Hey, one of the best performance models I've heard of is you can tell how far things will drop off by the unique number of pages that each query needs to access, based on the fuel maybe in memory as you start to grow. So if you have very large index trees from having large primary keys, you might have that problem. Or if you follow a secondary key to a primary key, and there are lots of values that were, as a non-unique secondary key, lots of values that resulted. Following those pointers to the primary key, you might have to load up lots of different random pages, and you can have a big performance drop-off.
Yeah. All right, so we're about 5 minutes. So does anyone else want to kind of say anything on primary keys, secondary keys, kind of stuff, or should we start wrapping up?
I wanted to mention one thing when you guys were talking about it before. There's something that's worth noting. Everybody says add a primary key, and if there isn't a primary key, then InnoDB auto creates one in the background. There's a problem with those ones that get auto created in the background, in which with a normal primary key that has an auto increment against it, the auto increment is locked individually for each of the tables. That's what this auto inc lock stuff is in InnoDB. But for tables that don't have a primary key, they actually use a shared structure that increments the values that get put in them across all of those tables. And that shared structure is a concurrency issue as well. So it's not really just good practice to add a primary key. It's actually, under the covers, you can't recognize it, right? But it's there, and the problem's there. Under the covers, it's a concurrency problem for every single table that doesn't have a primary key as well.
Mutex contention between the tables inserting your...
Yep. And I'm pretty sure that hasn't been fixed. It's been there a long time.
Shameless plug. With Common Schema, you have the no PK InnoDB tables view, which will let you know about any InnoDB table that doesn't have a predefined primary key. Use it.
First thing you should use at a new job. Thanks very much about that, Mark. And I didn't even know that. It's kind of scary that there's a shared data structure across all tables that don't have PKs defined. So define your primary keys.
Just to increment the values, right? It's just a shared counter that they all use to grab their values from, as I understand.
Yeah. So yeah, again, Mark says use primary keys. Alrighty, so we've got 2 minutes left. I want to open up for some topic solicitation. Morgan, I do want to hear about spatial indexes, so I think maybe next time, or potentially.
Yeah, we can talk about index fragmentation, stuff like that.
Yeah, I don't want to describe it myself because I'll probably butcher it more than I did insert buffer. I'll see if we can get someone from the
change buffer.
Describe that better. Change buffer, yes.
Change buffer.
Yeah, it has been updated in old documentation to call it change buffering. I have to get with the times of the last 5 years.
Tell me about it.
So should I rewrite my notes to say change buffer instead of insert buffer?
It has to say change buffer, yeah.
Yeah, in source code it still refers to an insert buffer, I believe, but that's maybe not go there.
Yeah, I thought your drawing was awesome, Morgan, where you did an update statement and then you said it's the insert buffer.
Just make it the CRUD buffer.
I practiced that in a few minutes this morning.
Right, you guys done?
I think we're all set. So yeah, Shlomi, you said index fragmentation. Morgan, hopefully we can get someone on spatial indexes. I've got a few things from Jerry. I talked to him earlier today, and so there's some stuff that he wanted to ask about NFS actually, and just other people who have had to use NFS and interesting problems that have been encountered there. I cringed personally when he said that. I've never used NFS with MySQL. I don't want to, but I understand that there are reasons to do it. Anything else? Mark, Morgan, anything else you guys would want to talk about in future sessions?
Out of left field, I think when you ask database administrators about networking problems, a lot of us have blank faces. I'd be curious, because I'm not strong on that, what advice people have.
Okay. About triaging network issues that you observe on the database, or?
Yeah, and what a database administrator should know about networking.
Okay. That's a really good one. Anything else from you, Mark?
No, nothing specific, really.
Okay. All right. Well, that sounds good then. I think we're out of time. Thanks very much for making it today, guys, and we'll see you next time in 2 weeks.
I'm going to be
See you
on
guys.
vacation next time, actually, so I'll see you guys when I get back.
Enjoy.
See you later, guys.
Take care.
Bye.